Langlands, as I say, Langlands' article was based on 7 questions. And the first question is what we've been talking about. So what we've got is we've got a reductive group over a number field. We've got the L group. Sometimes one writes gamma E over F. We've got automorphic representation pi. Got the Adels. And sorry to just repeat this again, but then there exists a finite set of valuations, S, which contains S infinity of valuations V, such that IV is unramified. For any V not in S. And then, and in this case, IV then gives us something much more elementary, or seemingly elementary, a conjugacy class, C V, or C of pi V, a semi-simple conjugacy class. In the local L group, which is G hat, the connected component of the local L group is the same as the connected component of the global L group. It's the dual group G hat, semi-direct product, Galois group, EV over FV. And this has a conjugacy class simply because of this thing. It has a conjugacy class of embeddings in the global L group, which is G hat, Galois group, E over F. And recall that E is some Galois extension that you get to choose. If you're Langlands, or if you're working on Langlands, you get to choose what E is. It's some often quite large Galois extension. And so this is a semi-simple conjugacy class in here, whose image in this Galois group EV over FV is a very particular conjugacy class there, the Frobenius conjugacy class. Okay, so that's it. That's kind of the background. This is what Langlands talks about this. In fact, the first half of his article is setting all of this stuff up. The point being that a lot of this stuff had not been discovered, or had not at least been written up, and Langlands wrote, sketched along with his view that these things would be, the various things that went into this would be, weren't that difficult and would be written up by people who he knew was working on them soon. And so we just recall also that we then have from this stuff, and well, this would be for any finite dimensional representation R of the global L group. We have the product of local L functions, infinite product of L, V, S, pi, R. Where L, V, S, pi, R is L, S, pi, V, RV, RV being the restriction of R to the subgroup, the relevant subgroup, and just the usual business, 1 over the characteristic polynomial, 1 minus RV CV I QV to the minus S to the minus 1. Okay, so this is what we talked about, probably repeating several times in one way or another earlier in the course. But what we haven't really talked about, and this was part of Langlands' assertions right from the very beginning, so we also have, we do have here, we're only talking about the product of pi v's for almost all v. And so we have the remaining finite collection of irreducible representations. Pi v, irreducible representations of the complete local completion of G. And we also have the local L group. G L V, which is G hat EV over FB. Okay, so we have these things for the remaining places. All right, so Langlands' first question, which is basically this, but with this added to it. So I recall that he said right at the beginning of the article, he'd rather think of these things, and he formulated them as such. He'd rather think of these things as questions rather than conjectures, but they didn't take long for them to become conjectures in the eyes of the mathematical community. And so they will be as follows. But first of all, one also has to fix an additive character, something that is always behind these things. So one fixes a non-trivial additive character. That's, you've got the locally compact additive group of adels, and you want to identify its dual group not in Langlands' sense, but in the sense of old-fashioned abelian harmonic analysis. And to be able to do that, you got to fix an additive character. The same thing as you do with the additive group of reals, where you take e to the I pi y. Well, that's what we're doing here. A non-trivial additive character psi from F star, A star into C star with restriction psi v to any given completion of this number field. So this is an additive character on the multiplicative group with these restrictions. All right, so that's the background for the various questions that then arose from Langlands' exposition. Well, I want, I'm sorry, quotient by F star. I want it to be trivial on F star. So I want it to be a character that's trivial on F star. But then what's relevant is its restriction to the various completions. Okay, so question 1. Is it possible to define local? Okay, we've got L functions up here in for the unramified places. Is it possible to define local L functions? And what's trickier, local epsilon factors. So local L functions, I forgot a line here, L V S I R and local epsilon factors. Epsilon V S pi R, and these are going to depend on the local additive character psi v. So this would be epsilon s pi v rv psi v, and their behavior. What's particularly important for these things is not their behavior as a function of s. That would be expected to be quite simple. It should be these as a function of s. These should be of the explicit form epsilon pi v rv psi v. That's just a complex number times qv to the minus nv. That's an integer, minus 1/2 nv minus 1/2 s. So when s equals 1/2, in other words, when s equals 1/2, this epsilon function should be equal to this epsilon factor, and then for a more general s, it should be extended in this simple way. So what's really relevant here is what that complex number is. And so the point is, this would be for all v. Such that the full global L function, L s pi r, remember these this finite set of valuations includes the Archimedean valuations. They're not just the ramified p-adic valuations, and they would have to be put into the L function. Langlands' notation here differed from the prevailing notation, I think, at the time, that L functions would be a product over all primes, but not the Archimedean primes. maybe people will upper lambda for the function that you get when you put in the Archimedean places. But in any case, with this notation, you're asking for an L function that's a finite product over the primes in S, together with this infinite product upper S that converges only in some right half plane there. That's what we've got up there. S pi r. In other words, this would be a product over all V, with all valuations of L, V, S pi r. And so is it possible to define these local L functions everywhere, and these local epsilon factors at all V, such that this thing okay, so this is just one sentence. Is it possible to define blah, 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 such that that complete global product has analytic continuation? It's understood that the L function, even just defined for almost all V, is analytic in a right half plane, which we've already talked about. But this has analytic continuation to S any complex number. And I guess this isn't quite correct what I'm about to say, but except for, I guess it's correct for my limited definition of automorphic representation as a constituent of L2 of GA over GQ, interpreted in a suitably narrow fashion. So with that, then except for a possible pole, at S equals 1, if the dimension of G is 1. I'm assuming here that this is something that occurs in the discrete spectrum and even is a cuspidal automorphic representation. And satisfies. Okay, so the assertion is, can you put in these extra factors in such a way that the resulting thing has analytic continuation? Well, these extra factors are going to be meromorphic functions themselves. So what's really relevant is the analytic continuation of that one up there. But now what's relevant to all of them is that it's supposed to satisfy a functional equation L of S I R equals epsilon S pi R L of 1 minus S pi R contragradient. This would be for epsilon S pi R being the product over all V in S of these epsilon factors epsilon V, S, I, R, psi F, psi equals psi F. The understanding being that these global epsilon factors are going to be 1 at the unramified places. So they're things that you put in at the ramified places, and they at the local places, each of these ramified places, they will depend on the choice of the additive character, but the product, finite product, will not. Okay, so that's the assertion. And I'll just say note. Our check G, this is a representation of the L group. So that's R of G transpose inverse. That's the contragradient. Representation. And while I'll repeat what I just said, while the global L factor, the global epsilon factor, epsilon V, the global epsilon factor epsilon S, I, R should be independent. Of psi. And the local epsilon factor epsilon V would be 1. If V is unramified. So with that understanding, we could write this as just simply the product over all V, with the understanding that if V is not in S, it's 1. All right, so that is the assertion of question 1. So I'm gonna be compulsive here. We'll underline this just so it's clear. This is what was intended to this, and then this was intended to be a lead to everything. All right, so yes. Pardon me? I'm assuming that an automorphic representation is, when I'm saying it occurs in L2 of GA over GQ, I'm weaseling here, that it's in the discrete spectrum, and that in fact, moreover, it is in the cuspidal discrete spectrum, the big piece. I mean, we could, it would take, we could have it would take a couple of lectures to actually say what the precise definition is, and then you'd have to, yeah.
In this epsilon factor, we're saying that there is no, you don't have to doctor it with 2 to the power something.
Well, I think we've got that, don't we?
But here you're saying epsilon S pi r is a product of the local epsilon factor.
This is how it behaves at any given place. This is,
okay.
yeah. And what's relevant, this is basically trivial, but what's deep and relevant, and it seems it's confusing. It certainly confused people that weren't hardcore algebraic number theorists, I think, when they read Langlands' first question, that what's important and difficult is that number, just that number. What is it? Yes. So I'll say a word about, no, I'll say partly, yeah, Tate and Hecke. But let me, yeah, there's what motivated this. Okay, so Langlands' strategy so Langlands' idea was to frame everything, all of what became the Langlands program. His idea was to frame it all in terms of L functions. L functions are certainly part of it, but they were a convenient way to phrase all of the questions just as they are wrapped up in terms of these L functions. In terms of L functions. So question 1 was meant to lead this way, that is to say, in terms of L functions, naturally into the other 6 questions. So as we know, we took functoriality as the core of the Langlands program, but as we know, functoriality can basically be phrased as a question about these L functions, and so that's in fact the way Langlands did it. And this was motivated. I'm not talking about the epsilon factors at this moment, but the introduction of the L functions. This was motivated, which you probably know, this was motivated in terms of not the discrete spectrum for L2 of GA over GQ or GF, but rather the continuous spectrum. Before this, Langlands had completely constructed, as I've mentioned earlier, he completely constructed the continuous spectrum, nothing about any of this stuff, but he constructed the continuous spectrum of L2 of GA over GF, something that's big and relevant, especially in the case of GLN, and he constructed the complete spectral decomposition of the continuous spectrum modulo an understanding of the discrete spectrum for Levy subgroups. And so this was motivated. It was called motivated or suggested, let's say. So it was suggested to him by his earlier theory of Eisenstein series. As he's giving the continuous spectrum. I ending up repeating myself. I said it and then I'm repeating it. The continuous spectrum of L2 GF over GA. And the thing is that this is in terms of what are called Eisenstein Eisenstein series, and it was a real breakthrough actually. Before any of this, I won't be talking about Eisenstein series, but E of x, B lambda, x would be an element in GA. GF. Phi would be an element in a representation space, an induced representation space. This would be an element in the in the Hilbert space on which the induced representation from P A to GA of the discrete spectrum of MF over MA. I'm running out of space here. It makes it more complicated. A. Okay, so that this is a parabolic subgroup. That's parabolic, and this is Levy component. So P equals MN is a parabolic subgroup. And write this down, but this is O and lambda is an element in the split component of M, the split component of the center of M, or in the language of Harish-Chandra, it's an element in a complex vector space, which is part of this induced representation. I didn't write this down, but it's the sum, I hope I get this right, over PF mod GF of phi I shouldn't I'm just going to say it's a sum of something in the Hilbert space on which the induced representation acts, and it is summed over GF modulo PF, excuse me, to make it be a function on X, which is invariant under GF rather than PF. So there's something in here that's in the discrete spectrum or the induced representation attached to this Levy subgroup, the discrete spectrum of this Levy subgroup. So it's basically a function on GA modulo PF, not GF, but PF. And so it's just simply a sum over this, which is done in order to make it invariant under GF. And so that this I don't want to, I will. So I don't know if this is visible, but a couple of just things to say. E of x, phi, and lambda is the analog of e to the x lambda in Fourier transforms. Where lambda is not a purely imaginary number, but rather a complex number. That's of no relevance at all in ordinary theory of Fourier transforms. You just take lambda to be is, and so it really is like e to the 2 pi, or just is, s being a real variable, x. And then it's a kernel that gives you that goes from the space you're interested in, L2 of R, additive group of R, to its spectral decomposition, in the case of Fourier transforms, which is purely continuous, and the mapping from L2 of R that you want to, whose spectral decomposition you want to exhibit by the Fourier transform into a direct integral of irreducible representations, in this case, e to the isx, is the mapping from one to the other is the Fourier transform. The mapping here is the exact same thing, except with a more complicated kernel, e to the x lambda. And so this really can be regarded as an intertwining operator between L2 of GA over GF and the induced representation of GA given by inducing, parabolically inducing the discrete spectrum on this Levy subgroup. That's what it is. It's just, formally, it's like this. But it's ever so much more complicated because this thing only converges in a right half plane, real part of lambda large. And so you're interested not in the real part of lambda being large, you're interested in purely imaginary values of lambda. So what Langlands had to do was to analytically continue this function of lambda. It converged in some right half plane. It had to analytically continue it to purely imaginary values, and then prove that with that purely imaginary lambda valued function as a function of x and lambda, and then this in the Hilbert space of the induced, of the discrete spectrum on the Levy subgroup, you had to use that as a kernel in exactly the same way that the function e to the I lambda x is used in Fourier analysis. But Langlands had to prove that this thing really gave you, as you let p vary over the finite set of parabolic subgroups with their discrete spectrum, and you let lambda range over the appropriate imaginary real vector space of imaginary values, that actually, so it's an intertwining operator. It's the kernel. The kernel of a mapping that's the exact analog of Fourier transform. So it's the kernel of an intertwining operator from it goes both ways. It just like Fourier transform, there's a Fourier transform and an inverse Fourier transform. Here we've got an Eisenstein series, and it's basically, roughly speaking, its complex conjugate is its inverse. But either way, it's an intertwining operator from L2 GF modulo GA. But the continuous spectrum of that and the induced representation from P to G of L2 discrete M A, the discrete spectrum of MF modulo MA, tensor e to the lambda h of x. I'm using notation that is easy to look up. Tensor. So if you're familiar with this terminology, it's really the discrete spectrum, not of all of MA, but M of A with the split component of the center thrown away. And then you put the split component of the center back in here with a purely imaginary lambda. And then you have the identity representation of NA. Okay, so P equals PA equals MA1 tensor e to the I lambda h of x tensor NA. So if you're not familiar with this, it's a purely formal thing. This is an induced representation. It's a purely formal thing, but it's just it's exactly what one would want if you asked for yourself, I want to exhibit the continuous spectrum of L2 of GA over GF as a direct integral of the discrete spectra of the Levy components induced the discrete spectrum of Levy components of parabolic subgroups induced from the parabolic subgroup up to G. Okay, so I'm saying more here than I had intended, but the point was that series, you can't even talk about this until you have this kernel. In Fourier analysis, it's just given to you. It's e to the I lambda x. Here, it's some complicated function of lambda and x and phi, which is given to you by a converging series in some right half plane in lambda. And you have to analytically continue it, and it's very deep and difficult to analytically continue that function of lambda from the real part of lambda large to the real part of lambda equals 0. And then you have to be able to understand how this intertwining operator breaks down and gives you right on the nose the continuous spectrum of L2 of GA over GQ. And so I guess I have a book. I think Langlands didn't write it in these terms. He didn't express it in these terms, but I have a book on the introduction to the trace formula. And there's one chapter that explains this better than I have done here. And I also wrote an article in the Corvallis Proceedings. That states exactly in better and clearer terms, I hope, than what I've said here. That's exactly what Eisenstein series gives. So this was a prelude. The point is that these Eisenstein series, you need to know, for what Langlands was doing, you need to know what happens when x is an element Um, you need to know what happens when x equals n a m. This is in m, this is in a, and this is in n. And you need to know what this looks like when a gets very large. You need to understand its behavior at infinity, it turns out. And the formula for this thing has, well, first of all, this thing has an analytic, this thing has a functional equation in terms of an intertwining operator, ms of lambda, that goes between the induced representation between lambda I think I'm just going to confuse it more if I try to write this down without a very careful statement, get rid of confusing points, but it's all explained, I hope, clearly in either of these things. There's an intertwining operator. This thing satisfies a functional equation which takes place when lambda is replaced by a Weil group translate of it. And you get an operator on this space of phi's that Langlands writes as M. Maybe I should write it as W. W is an element in the Weil group. But the thing about it is that this thing, the main part of this thing is a quotient of two L functions, two automorphic L functions. They are, excuse me, they are automorphic functions that come from M. You've got M, and it comes from the adjoint so M is a Levy subgroup. It has a discrete spectrum. It has cusp forms, well, maybe we better just say discrete spectrum, because cusp forms can be a little problematic if you're not dealing with GLN. But in any case, you have the discrete spectrum here, but you also have a representation of what turned out to be the dual group of M on the Lie algebra of N, the unipotent radical. And this thing, the functional equation of this thing, had in it, the main terms in it were a quotient, actually, of automorphic L functions attached to discrete, cuspidal discrete representations of M, and a representation of the dual group acting on the Lie algebra of N. These terms had not been invented yet, but that's what they turned out to be. And Langlands saw that. He saw that this operator satisfied its own functional equation, and he looked at it, and it was a special case then of these general automorphic L functions. And the functional equation that this thing satisfied was, first of all, its analytic continuation was part of the proof of Langlands' analytic continuation of this thing. And the functional equation that this satisfies, and that this satisfies its own functional equation, is highly suggestive of the function of is highly suggestive of the general functional equation of these things. So in short, this thing has what turned out to be automorphic L functions for M, and the representation of the L group of M on the Lie algebra of the unipotent radical. And the analytic continuation of these things included the analytic continuation of those L functions. It didn't quite include the functional equation, but it was consistent and very suggestive of the functional equation. And so this was enough to motivate Langlands for well, a lot of this stuff here. Just solving a completely separate problem in spectral theory. These things, by the way, I think physicists call these things, or the analogs of these things in physics, scattering matrices. These functions m of s lambda.
Use the same letter for the Levy component as well as the function m and n.
Little m.
The Levy component is also capital M.
Yes. Well, we've got the Levy component, and then we've got the functions on the Levy component. It's where do we have the other thing?
M, W, lambda.
Oh, yes, you're right. So he used that. Maybe I can't remember if he wrote L for the Levy component. Yeah, it's a bit confusing, but that's.
But then that could have its own problems.
yeah, that's right. So I
So, as I understand for lambda, the unipotent part does play a part. I didn't understand the notation. Where does lambda live? Lambda lives in something star and C.
well, it's like GLN. It's like M. It's as if M were something like the general linear or product of general linear groups if you're dealing with GLN. And then there's no discrete spectrum for GLN because there's an infinite central component to it. So if you want to talk about the discrete spectrum, you have to take off the discrete spectrum. And that's what this one means. You get rid of the split component of the center of this thing and then look at the discrete spectrum of what remains. If you take that off, then it's a finite volume. And then, but then you got to put it back in. This is where the continuous spectrum comes in. So you have to put in the lambda, which parameterizes the spectrum of the split component, the spectrum of the center of this thing. And so if this is a small Levy subgroup, there's several, it's higher dimensional. Lambda is a higher dimensional thing. You might ask, where do you get L functions out of that? But you're taking an inner product of lambda with roots, so they really do have one-dimensional pieces to them. I'm sorry, I think I may have confusing it a little bit, but anyway, it was, this was a huge breakthrough.